I'm Casey Jessop. I'm a PhD student from Chalmers University of Technology, and the title of my presentation today is Friction Between Pearlitic Steel Surfaces. So as we've heard from a lot of talks in the last few days, tribology is a very important aspect to consider in the railway industry. With the varying temperature and climatic conditions that you find out in the field, of course, this has a big impact on the contact between wheel and rail materials, which we've heard quite a lot about, but my focus is more on the crack face friction. So in my PhD project, I'm looking at damage and defects in railway materials, and the purpose is to be able to, at some point, grow cracks in similar conditions that you might find in field. So I have here a picture, okay, there's no pointer, of a squat crack, which has been broken apart. And what we see here is these sort of ridge formations. So within the geometry, you have a first big geometry of the crack network, but on a smaller scale, we've investigated a lot this topography. So we think that, or I guess it is, the crack face friction has an impact on how these cracks are growing and how you have, for example, these ridge formations. So yeah, the crack face friction is important in part with the crack closure. So when you have these ridges or asperities, then you're not having perfect contact between the surfaces. Also, since squat and squat-tight defects are surface initiated, they have surface breaking cracks, and then the influence of the environment is, of course, gonna contribute to how the cracks are propagating. Yeah, so finally, the crack propagation. So what we did as a study, sort of pre-study towards crack propagation experiments, we have two steel surfaces, so pearlitic R260 steel. We've made the specimen so that the friction that's measured can be assumed to be coming purely from the contact between the two surfaces. So the motion of the two halves, the steel halves against each other, shouldn't be a factor within the friction. What we did, mounting these two halves inside the actual torsional test machine, the bottom half is rotated for different angles of rotation at different speeds, and compressive loads are added to be able to see the influence that these different parameters have on the measured friction coefficient. So I'll jump immediately into the results. The first thing that we noticed when running these tests was that there was a directional dependence between the friction coefficients, which are measured when the test bar is rotated with the first cycle, rotated in the clockwise and counterclockwise directions. So the clockwise, those that have the first cycle in the clockwise direction are the number 15 and number 18, so the blue and the green line here. And test number 16 and 17 were run respectively in the same conditions, and you see that their maximum coefficient of friction comes in also the clockwise direction. Also, in these two different sets of tests, the speed of rotation was varied, and we can see that that doesn't have much of an effect on the maximum and minimal values of the coefficient of friction. Furthermore, if you look at the test run with initially the clockwise rotation and the counterclockwise rotation, the wear and the deformation doesn't have any difference. So yeah, we basically attributed this to the initial surface roughness is just from the machine condition. So most likely, it's just the turning was done in one direction. And then this is affecting a little bit how easily the two halves are rotated against each other. Also, in terms of the different angles, we ran 2 tests here, with the main difference being, or both these tests were run for the same total sliding distance. So with a plus minus 0.5 degree rotation for 200 cycles, or plus minus 10 degrees for 50 cycles. What we can see from these results is that you still have a variation between each, during each rotation, but the directional dependence when you have small angles of rotation, which is what you see on the top graph here, is much less significant than when you have larger angles. Also, in terms of the wear and the deformation, we can see that when you have larger angles of rotation, the surface deforms a lot more. So we can see in these 2 test bars on the bottom, there's a lot more of this ridge formation, and also a lot more wear product, which is more powdery. In the small angles of rotation, the deformation is mostly on the inner contact radius, and the wear products are staying more or less inside the deformation which is happening there. In terms of the normal force, varying the normal force, an increase in the normal force or the compressive force which is applied decreases the variation within each rotation. Also, increasing the normal force decreases a little bit the difference in the maximum and the minimum values of coefficient of friction, which are calculated. So we see in this plot, the light blue is the lowest compressive force, and then the dark blue is in the middle, and then the black crosses are the highest compressive forces. And the values, the reason for these compressive forces is that basically just because of the equipment, I could not apply more than 8 kilonewtons without having lots of screeching. So this is as high as we could go within the equipment. Also, tests were run in dry and in wet conditions. For the wet conditions, the 2 test bars were set up and the compression load was added, and then afterwards water was added inside a funnel to sort of wet the surface of the test bar, but there was initially no water in the contact zone. What we can see is most evidently that the wet tests have lower coefficient of friction, which is to be expected. There's a lot more variation within the coefficient of friction in one single cycle, so there's a lot more of a slope. For example, in this test compared to the blue test up there. So, yeah, the orange and the blue have all the same conditions except for wet and dry, and the black and the turquoise have all the same conditions except dry and wet. Also, we can see in the surface that there's a lot more deformation inside the tests run in dry conditions, and there's a lot of accumulation of the wear products on the inside radius. As for the wet tests, the surface is barely deformed. You have some deformation and some wear that you can see on the inner radius of the test bars. Finally, if we look more specifically at the deformed surfaces that we have after the tests, so with increasing angles of rotation and increased compressive forces, we have more deformation occurring. And we can see that there was some sort of similar pattern that we can find, that we found in this squat here. In terms of the wear debris, if it wasn't just a powder that was at the middle, we can see that it's accumulating more or less randomly along the surface. It gets kind of blotchy in some parts, so there's no continuous distribution of it, and the angles of rotation, basically with larger angles, then you see more than with the smaller angles. So in summary, varying the rotation, the angles of rotation, and also the rotation speed, we can see that there appears to be a directional dependence. So repeated twisting of the two steel surfaces led to the formation of asperities, or I would call them these ridges on the surface. These were, of course, influenced by the initial machined surface. So if tests are going to be repeated, probably trying to have lower roughness and see what can happen in that case. Compressive forces and the twisting motion imposes preferential deformation of the materials, and increasing the angles of rotation increases the formation of ridges and also leads to higher maximum coefficients of friction. Increasing the normal force decreases the variation between the coefficients of friction, and the directional dependence is less significant. Dry versus wet conditions, the water decreases the coefficient of friction, and this leads to less wear and a smoother, uniform deformation of the surfaces. And finally, the initial smooth finish leads to initially lower coefficient of friction, but after some run in time, the coefficient increases and basically stabilizes. So to conclude, the effect of the crack face friction on crack propagation is an important issue, and it requires still further investigation. The results from this study are hopefully going to provide some more information in terms of crack face friction for crack propagation experiments, which are going to be upcoming in my work. So, thank you for your attention.
Thank you.